Hello everyone, and welcome to our channel. Today, we are diving into something deeply fascinating, the GSM Symbolic project, a groundbreaking exploration of the limits of mathematical reasoning in large language models. If you're interested in artificial intelligence, the intricacies of model performance, and the future of AI reasoning, you've come to the right place. Stick with us as we break down what GSM Symbolic is, why it's crucial, and what it tells us about the capabilities and challenges of today's AI systems. And for those who are new here, don't worry. We'll guide you through everything step by step, so by the end of this video, you'll be well informed about the breakthroughs and the challenges in AI model reasoning. If you enjoy this deep dive, remember to like the video, comment with your thoughts, and subscribe to stay updated with our latest content. So, what is GSM Symbolic, and why is it important? GSM Symbolic is an advanced benchmark created by Apple researchers to explore the mathematical reasoning abilities of large language models, LLMs. You may have heard of GSM 8K, a popular benchmark used to evaluate how well AI models can solve math problems. GSM Symbolic takes things a step further by using symbolic templates to generate a broader, more diverse set of math questions. This approach allows for more detailed, controllable evaluations, providing insights into whether models are genuinely reasoning or simply mimicking what they learned during training. The fundamental issue the researchers wanted to explore is whether large language models are truly capable of logical reasoning. Imagine you ask an AI model a simple grade school math question, and it answers correctly. That's impressive, right? However, here's the catch. The researchers wanted to see if changing some numbers or adding irrelevant information would confuse the model. And guess what? It often did. One of the core concepts behind GSM Symbolic is to test the robustness of AI models by presenting them with different versions of the same question. For instance, a problem might have its numbers changed, or irrelevant details might be added to see how well the model can focus on what truly matters. This helps evaluate if the model understands the mathematical principles or if it's just relying on pattern recognition without genuine comprehension. One of the most exciting aspects of the GSM Symbolic project is that it exposed significant weaknesses in current models. When researchers slightly altered the numbers in a question or added extra, seemingly relevant, however, ultimately inconsequential information, the model's performance dropped dramatically. This finding suggests that many models aren't reasoning in a way we humans would recognize. They're essentially relying on patterns from their training data. For example, let's say we have a math question involving a few numbers, and then we add a sentence about how 5 of the items were slightly smaller than average. Many models, rather than ignoring this irrelevant detail, tried to integrate it into their calculations, which led to incorrect answers. This phenomenon was termed GSM no-op, a special set of experiments where irrelevant information was added to questions, making the reasoning process much more challenging for the models. Now, let's break down how GSM Symbolic works. This new benchmark generates variants of math problems using symbolic templates. For instance, a problem like, how many toys does Sophie have if she adds X amount, could be generated in numerous forms by just changing variables like the names, values, and specific items mentioned. This approach reveals whether AI models understand the core reasoning or just memorize patterns. The goal here is to have a dataset where the difficulty and details can be varied, giving us a better measure of a model's true abilities. The findings showed that models were much more fragile than initially thought. For instance, even small changes in the problem, such as swapping numbers or adding extra, non-essential information, caused significant drops in performance. It seemed that the models were not robust in their reasoning abilities. However, they were somewhat susceptible to these changes. This implies that current AI models are often performing a kind of advanced guesswork rather than truly understanding the problem they're solving. Now, let's move on to the experiments and results section of this benchmark. One of the significant tests was to see how models would perform when faced with simple variations in the same question. The researchers generated questions by changing just the names or numbers involved. The results were eye-opening. While models could handle changes in names reasonably well, altering the numerical values led to a drastic drop in accuracy. In one experiment, a model's performance dropped by more than 15% just because of changes in numbers. The researchers also tested how models reacted to an increase in question complexity. They found that as they added more clauses or increased the difficulty of questions, the model's accuracy decreased, and the variability in their performance went up. This again suggests that the reasoning capabilities of these models are not as robust as we might hope. One of the most dramatic findings came from what they called the GSM no-op dataset. Here, they added clauses that seemed relevant, however, were actually unnecessary for solving the problem. For example, a sentence like, "Of the items, some were smaller than the average," was added to see if models would correctly ignore it. Unfortunately, most models failed. They treated this information as if it were crucial, which led to incorrect conclusions. This performance drop was up to 65% in some cases, which shows that the models were not distinguishing relevant from irrelevant information. This brings us to the implications of the GSM symbolic findings. The key takeaway here is that LLMs, even those trained on vast amounts of data and capable of answering a wide range of questions, struggle with what we consider real reasoning. They're excellent at mimicking patterns they've seen during training. However, they are fragile when faced with changes that require true logical understanding. This fragility means that while LLMs can be very useful, we need to be cautious in how we deploy them for tasks that require critical reasoning, particularly in areas like education, decision-making, and critical infrastructure. The researchers pointed out that these models' reasoning is less about genuine understanding and more akin to probabilistic pattern matching. They look for the closest matching problem and apply similar steps to solve it. This works well until you slightly change the problem, and then the model struggles. Why is robust reasoning important? So, why is this so important? Robust reasoning is crucial for any AI system that we want to rely on in complex and sensitive scenarios. Imagine using AI to assist in legal decisions, medical diagnoses, or emergency responses. In these scenarios, it's not enough for the AI to make a good guess. It needs to understand the nuances of the problem to make sound, reliable decisions. The fragility shown by LLMs in the GSM Symbolic benchmark suggests that they are far from ready to handle such responsibilities. Another critical aspect is trust. When we use AI systems for critical tasks, we need to trust that they can handle the unexpected. Real-world scenarios are rarely as clean and straightforward as the training examples these models see. Changes in context, the presence of irrelevant information, and evolving dynamics all mean that an AI system has to adapt. The GSM symbolic findings show that current models are limited in this capacity, which directly impacts how much we can trust them in real-world applications. The results of the GSM symbolic benchmark are a reminder that we have to be mindful of the gap between performance in benchmarks and real-world utility. When models perform well on benchmarks like GSM 8K, it's easy to assume that they are competent reasoners. However, benchmarks are controlled environments, and the GSM Symbolic project demonstrated just how quickly models fall apart when the control is lifted, when the details change slightly, or when complexity is increased. How can we improve AI reasoning? The big question, then, is how do we improve these models? How do we build systems that can genuinely reason and are not just regurgitating patterns they've seen before? One promising approach is structured training. Researchers suggest that if we can train models in a more structured manner, focusing on developing symbolic reasoning abilities rather than just feeding them vast amounts of text, they might be able to better generalize across different problem domains. Instead of learning by exposure, models could learn by actually practicing logical reasoning, much like how a student learns mathematics by working through problems that require understanding, not just memorization. Another method could involve multimodal learning. By training models to reason across different types of data, text, images, videos, and even real-world interactions, they might develop a better sense of context and relevance. In human learning, we often apply knowledge gained in one domain to another, and multimodal learning might help AI systems bridge similar gaps. In addition, prompt engineering and fine-tuning on targeted datasets can improve performance. Researchers found that when they specifically fine-tuned models to deal with more complex variations of questions, they performed somewhat better. However, this approach also has limitations. It's essentially making the models more accustomed to specific scenarios rather than fundamentally changing their ability to reason. Thus, while these techniques are helpful, they are not a complete solution. Another area for improvement is robust evaluation. GSM Symbolic itself is a step in the right direction because it highlights the importance of evaluating models with diverse and challenging datasets. To better understand how capable a model truly is, we need to assess it in environments that simulate the messiness of real life, environments that are unpredictable, filled with irrelevant information, and constantly changing. The path forward involves developing new architectures, improving training paradigms, and focusing on evaluation metrics that better capture the model's reasoning ability. The GSM Symbolic project shows us that the answer isn't just in bigger models or more data, it's in how we think about building and training these models from the ground up. There is also an ongoing conversation about incorporating human-like reasoning into AI systems. Some researchers are exploring the use of neurosymbolic approaches, which combine the strengths of neural networks with more traditional, symbolic logic systems. By embedding symbolic reasoning into these models, they might become more adept at solving problems that require logical thinking rather than just pattern recognition. As AI developers, we must also consider transparency and interpretability. For humans to trust AI, especially when it comes to high-stakes decisions, we must understand why a model made a particular choice. Current models, often described as black boxes, lack this kind of transparency. Improving our understanding of how models arrive at their conclusions can help build AI systems that are not only more capable but also more accountable. And there you have it. A deep dive into the GSM Symbolic project and what it reveals about the reasoning abilities of today's large language models. It's both a fascinating and cautionary look at where we are with AI technology. We're making incredible progress. However, there are still significant hurdles to overcome. If you found this exploration insightful, please give this video a thumbs up, share it with your friends, and don't forget to subscribe to our channel for more deep dives into AI, technology, and the future. We'd love to hear your thoughts in the comments below. Do you think AI can eventually master proper logical reasoning? Let us know what you think, and let's keep the conversation going. Thank you for joining us, and I'll see you in the following video.